Hey guys, it's Miss Gray. You made it through the first 2 units of AP Chemistry. Now let's start something new. In our last unit, Unit 2, we talked about the 5 basic types of reactions, and this time we're going to focus on only 2 types, acid-base reactions and redox reactions. So don't you worry, you're in good hands. I am a trained professional. First, we're going to learn how to determine the concentration of a solution and make measurements about concentrations and how to describe solutions. Then we'll distinguish between different types of acids and bases and talk about different theories of what an acid is and what is a base. Then we'll figure out how to use titration, so you'll be doing a lab and working with those calculations. And then finally we're going to move into redox reactions, identifying oxidizers, reducers, and then balancing and predicting the products of redox reactions. So hold on tight. Here we go. Let's start with the parts of solutions. First of all, we're going to know that a solution is a homogeneous mixture where the components are so thoroughly mixed that you cannot distinguish one particle from the other. It's the most homogeneous of all mixtures. We call the solute the thing that gets dissolved. And the solvent is the part of the solution that is doing the dissolving. So usually the solvent is some liquid, but not always. Sometimes the liquid gets dissolved in a gas, like a foam or even a cloud, is where liquid water droplets are dissolved in air. A soluble substance is something that can be dissolved, so we call that soluble. But if they're both liquids, then we call it miscible, because which one is really the solute or the solvent? We don't really distinguish, but we say they are miscible, whereas something like oil and water would be immiscible because they don't mix together. Well, let's focus on aqueous solutions. Aqueous solutions rely on specific properties of water. You see, here's a water molecule where we have an oxygen and a hydrogen. 2 hydrogens, that is. So oxygen has this partial negative charge because it's got 6 valence electrons around an oxygen, right? Yep, drawn dots. So hard. And then hydrogen donates another. And that hydrogen donated one. And so in the bond, we've got these 2 involved, and these 2 are involved in the bond, but then we have these lone pairs that belong to the oxygen alone. So it has more electron concentration around it, and the hydrogens have given up their electron to that bond. They don't have any to keep all to themselves, so they have what we call a partial positive charge. And this imbalance of charge makes water a polar molecule. See, these molecules get like a magnet with a north pole and a south pole, only it's a positive end and a negative end. The oxygen atoms have the negative side and the hydrogen atoms have the positive side. It's because the bond angle is so special. You see, this angle right here is 105 degrees. If it was like 90 degrees, then our vectors would cancel out and the positive on this side would cancel the positive on this side. But since it's 105, they don't cancel out, and so we end up establishing like a positive area here and a negative area on this side. So that's what makes water a polar molecule. And because it is, then we say we have this region where we have a positive charge and a region where we have a negative charge. That's an important feature of water. And let's see why. Clear it away. There we go. You see, dissolving depends on the process of hydration, which is where water molecules break the ions of a salt apart. Ions are made up of charged particles. Ionic compounds make salts, and salts are made up of charged particles. And the opposite charges attract. It's a law of physics. So let's say we've got our beaker here. Let me draw the rest of this picture in so it makes more sense. Alright, so we've got our beaker, and we put in there a heap of salt, right? And so what's going to happen is that water molecules are going to bump into the salt molecules. Well, depends on how they bump. If I bump a negative charge here, they're going to repel, but if I bump a positive charge here, then it's going to be attracted to that negative, and the negative is attracted to the positive, and some of those interactions are going to be pulling the negative charges away. Let me show you what I mean. Here's a water molecule, and that negative particle that was associated with the salt gets surrounded by the positive side of the water molecule, the hydrogen side, and so now it's being forced away or pulled away from the clump of salt. The same would happen to the positive particles, only those ones would be attracted to the negative end of the water molecule, the oxygen side. And then we would completely, once it's moved away from the salt, we would completely surround it with water molecules where opposite charges align. And this is the process of hydration. This is what it means to be dissolved, is that the particles get completely surrounded. And that's why they get mixed up so completely and so thoroughly, because the water completely surrounds every single particle in that salt. So that is the process of hydration. If water's not the solvent, then we simply call it solvation. Let me write that word down for you, solvation. It's the same as hydration, only it would be using some other solvent that's not water. So how would we describe the amount of stuff that we can dissolve in water? Typically we would report it in grams of that substance for every 100 milliliters, but it's more common to use molar or molarity, and I'll show you how that works in just a few slides. Solubility is going to vary, especially according to temperature. You've probably had the experience that if you heat up the water, generally speaking, you can dissolve more stuff in it. So solubility is going to vary according to temperature and some other factors too. But when ions are separated from one another or hydrated, that means they're free to move around. They are no longer bound into the crystalline structure of the salt, and they get to move. That's critical. Moving charges. We can use that. Water could also dissolve non-ionic compounds, but only if they have polar bonds. Completely non-polar, non-ionic compounds will not mix with water. So let's see. What are we going to do with these moving charges? You see, moving charges is electricity. If you can get a charge to move, you can generate an electrical current. The only ions that can move are those that are dissolved. And so a compound that will conduct an electrical current when it's in aqueous solution, we have a special name for these guys. They are called electrolytes. These guys are pretty important. That means they can conduct electricity. So we take advantage of that feature. So let's classify solutions using this particular property since it's so important. First, you would have your strong electrolyte. These are compounds that completely break apart into ions when mixed together with water. That means none of them stay bound up in their molecular form. All you get is ions. So we get a lot of ions, and that means a lot of particles that are free to move. These are very good conductors. They will light up the light bulb in the circuit. A weak electrolyte means that only some of the particles dissolve into ions, and the rest of them will stay together because they dissolve a little bit, but not very well. And so your light bulb here is going to be not very bright. Non-electrolytes, though, these ones don't break apart at all. Typically, our non-electrolytes are going to be organic compounds, like oil. It's an organic compound. Or sugar. Sugar dissolves in water, but it doesn't break into ions. They exist in molecules, and they don't conduct electricity at all. So your light bulb stays dark. If you will look to your solubility rules, you'll know which ones are strong electrolytes and which ones are non-electrolytes. Strong electrolytes means they are always soluble. So alkali metals, nitrates, chlorates, Knockle-no-so rules. You guys know these? And then the non-electrolytes are the ones that don't dissolve at all. So something like silver chloride would be considered a non-electrolyte because it doesn't ever dissolve in water. We already talked about this. Oh yeah, types of electrolytes. Here we go. Yeah, so there's a couple of important types of electrolytes that we're going to focus on in this unit in particular. Acids are those that form hydrogen ions when they are dissolved. So that's our definition of an acid. What type of ion is a hydrogen ion? Hydrogen ions are supercritical. They make acids, but they also make things happen in your body's cells. There's hydrogen ion pumps where electricity or energy is literally captured at the cell membrane every time a hydrogen ion goes through it. So strong acids are going to dissociate completely. That's why they're called strong. Like a strong electrolyte breaks apart completely, so do strong acids. You need to memorize 8 acids. All the other ones are weak, so you don't want to memorize all of the rest. You just memorize the strong ones, and then you'll know if it's not one of these, it's got to be a weak acid. So here's your first 3, sulfuric acid, nitric acid, and hydrochloric. Then there's hydrobromic and hydroiodic. Do you see a trend here? Binary acids. And then periodic, chloric, and perchloric acid. So memorize these 8 and you'll be set. Weak acids are those that do not dissociate completely. So they will make some hydrogen ions, but they'll also exist in molecular form in the water solution. So you'll get only a fraction of the molecules breaking apart. Bases are those compounds that form hydroxide ions when they dissolve in water. So a base and an acid combine to make water. That's why these reactions are very important to us. Strong bases are those that completely break apart. Again, they get split up into their ions. So here's the strong bases. Those that are formed from alkali metals, so lithium, sodium, potassium, cesium, and rubidium. And then 3 more, barium, strontium, and calcium. You've seen those guys, that gang of 3 before. So think back to your solubility rules. What's going to break apart? Alkali metals. You got it. And then in the hydroxide rule, remember which hydroxides are the exception? Barium, strontium, and calcium. That's your exception. So memorize your strong acids, memorize your strong bases. All other bases are weak bases, including ammonia. Most people think because it's a common base or an irritating base that it's necessarily a strong base, but it's not. There are lots of weak acids that can be very destructive too, like hydrofluoric acid can do a lot of damage, but it's not a strong acid because it doesn't dissociate completely in water. Okay, well let's talk about how to measure concentration. How much stuff is dissolved in your solution? Here's what we do for molarity. We take the moles of your solute divided by the liters of the solution, the complete solution, solute and solvent together. We use the abbreviation capital M, capitalization is important, and 1 molar means there's 1 mole of solute dissolved in 1 liter of solution. So let's look at a specific example. Let's calculate the molarity of a solution that has 34.6 grams of sodium chloride dissolved in 125 milliliters of solution. So for molarity, we need to have moles per liter. All right, seems simple, right? But I don't have moles yet. That's no big deal. You guys know our first step generally. When in doubt, we're going to go to moles. So we'll take our 34.6 grams of sodium chloride and change that to moles. 1 mole of sodium chloride has a mass of 58 or something like that. Let's see. Sodium 22.99. Works better when you turn it on. And then chlorine is 35.45. Yeah, 58.53 grams per mole. All right, now since I want moles per liter, I'm just going to keep my T-table going here. I want moles to be on top, and it is now because grams has canceled away. And I want liters to be on the bottom. Right now I have milliliters. We're dissolving in 125 milliliters of solution. So I'm putting it on the bottom. All right, but that's not liters. Well, it could be real easy. Move your decimal 3 times over. Now it's in liters. Now I have moles over liters, and I'm done with setting up my t-table because I got exactly what I wanted. 34.6 divided by 58.53, and then we'll divide that quotient by 0.125. So I get a molarity here of 4.729. How many sig figs? Looks like 3 sig figs. So 4.73 molar sodium chloride. Put your answer in a box, please. And that's how we do it. That's not so bad. Moles. Go to moles, and then put your liters on the bottom. Make sure, though, that you know how to change milliliters to liters. It's going to come in handy for you to just know how to do that by moving the decimal so that you don't have to include that in your t-table every single time. All right, so here we are again. Molarity is equal to moles of solute divided by the volume of solution in liters. You're going to use this a lot, molarity, moles over liters. For instance, if I have a 6 molar solution of hydrochloric acid, that means there's 6 moles of hydrochloric acid in every 1 liter of hydrochloric acid. So, what's our ion concentration? You see, hydrochloric acid is one of those strong acids, right? And so we're going to have HCl in water break apart into ions. None of them stay together. So we'll get hydrogen ions and chlorine ions. For every 1 hydrochloric acid, we get 1 hydrogen and 1 chloride. So our ion concentration then is, for every 6 molar HCl, we get 6 molar hydrogen ions and 6 molar chloride ions. That seems pretty logical, but let's do another one that's a little trickier. If I had sodium sulfate, then when this breaks apart, 1 sodium sulfate is going to break apart into these ions. I'm going to get 2 sodiums and 1 sulfate, right? Because in this compound there's 2 sodiums for every 1 sulfate. So that means in 6 molar sodium sulfate I get 6 molar sulfate ions, but my sodium ions are going to be 12 molar sodium ions because I get twice as many sodiums as I do sulfates. Okay? Pay attention to your stoichiometry. It will sure help. Okay, let's do an example. We can use molarity in a t-table for a conversion factor because we have moles over liters. Well, you can flip that over and have liters over moles. As long as you put the numbers in the right place, you can do it any way that you need to work out your units. So we want to know how many moles of nitric acid are in 2 liter solution of 0.2 molar nitric acid. So we're going to start with what we know. We have 0.2 moles per liter. That's what molar means, right? Means moles over liters. So 0.200 moles in every 1 liter of nitric acid. And how much do we have? 2 liters. I'm going to put that in my t-table so that liters cancels out. Okay, so we know we have 0.2 times 2 is 0.400 moles of nitric acid in that solution. That's it. Piece of cake, huh? Sure. Well, if it's not a piece of cake, try it again. Okay, here's our next example. What volume of solution is necessary to provide 2 moles of nitric acid if we're starting with a solution of 0.30 molar nitric acid? Okay, so let's start with what we know. We know we have 0.30 moles. Nope, let's start with 2 moles. We have 2 moles And our solution is 0.30 molar. I'm going to put this T table together so that moles cancels. So I put the moles on the bottom and liters on the top. Again, molarity is moles per liter. So where it's a capital M, I'm just translating that directly into moles over liters. Okay? So now I multiply across the top and divide by the bottom. So it's 2 divided by 0.3. We're going to need 6.67, 2 sig figs, 2.7 liters. Wow, I said 2.7, huh? 6.7 liters of this solution so that we can provide 2 moles of nitric acid. There we go. All right, suppose we need to go not to moles or to liters, but we've got to get to mass now. No problem. We know how to go from moles to mass, so when in doubt, we're going to moles still. All right, how many grams of solute? Grams is our goal. Are present in 50 milliliters of 0.360 molar. So I'm going to start with the 50 milliliters. And let's change that to liters real quick. 1, 2, 3 moves. All right, so in 0.050 liters. And what's our concentration? We better put liters on the bottom for every 1 liter. I have 0.360 moles. Great. So now we're going to change moles to grams. For every 1 mole of potassium dichromate, how many grams do we have? I'm going to need my calculator and my periodic table. So let's see. Okay, so I'm getting a molar mass of 294.2 grams. You let me know if you got something different, okay? And then let's work out our T table. So 0.050 times 0.36 times 294.2, and I get 5 let's go with 3 sig figs here. So 5.30 grams of potassium dichromate. Okay, put your answer in a box, please. So that's how we use molarity as a conversion factor. We put it in our T table in a way that cancels what we don't want and gets us closer, gets us to moles, so we can get what we do want. Oh, we got another example to do. Man, it's like I really want you to know how to solve these or something. Okay, so now we have 4.28 grams of ammonium sulfate dissolved in enough water to form 300 milliliters of solution. Notice, we may not have 300 milliliters of water in this solution because some of that space is taken up by the ammonium sulfate. So remember, molarity is moles of solute divided by liters of solution, not liters of solvent. Okay, we want to get to moles per liter. So let's start off with grams, 4.28 grams. And this is ammonium sulfate. So we're going to have to work out that molar mass. We'll put grams on the bottom and moles on the top. So we'll do that here in a second. Then how many grams are in a mole. And now we have moles on top. All I've got to do now is put liters on the bottom, right? I want moles per liter as my target. So if I've got moles, now I need liters. And I have 300 milliliters. And if I move that decimal 3 times to the left, I got it. It's okay to have this blank up here, to not have a number there. That's allowed. You're allowed to do that. Okay, so the molar mass of ammonium sulfate is 132.15 grams. Okay, looks good. Let's put it in our T table, crank it through the math, get your calculator out. All right, I get a molarity of 0.1107, yeah, 0.1 molar. I only get to keep one sig fig because that value has only one significant digit. So I get 0.1 molar ammonium sulfate. There we go. All right, gee whiz, how many more examples did I put in here? Gosh, that's all right, we'll keep it going. How many milliliters do we have of a 0.240 molar copper sulfate solution? And it's going to have 2.25 grams of solute. So I got to know how many moles that is, yeah? 2.25 grams. And this is copper sulfate. So let's see. Sulfate is 96, and then add copper to it. Oh, I forgot a decimal place. That'll mess you up. Okay, 159.62 grams per mole. Okay, now let's put molarity in here. Remember molarity? Capital M stands for moles for every 1 liter. So I can put moles down here, but I got to bring that number with it. 0.240 moles for every 1 liter. All right, and then of course I'm going to change milliliters to liters. Every liter has 1,000 milliliters in it. When I get to that part of the math, I'm just going to move the decimal, but you can do it any way you like. Okay, so I get 0.0587 liters. That's going to be 58.7 liters. Do I get to keep all 3 sig figs? Yep, I sure do. 58.7 milliliters of solution. Great. So now you've seen several different ways to use molarity in your T-table so that you can change moles to liters and liters to moles. Pretty handy. Let's talk about preparing solutions. Here's what you're going to do in your labs, and you may already have done this by now. You will weigh out your solute on the balance and then carefully put it all into your volumetric flask. I usually add water first, a little bit of water first before I put the dry powder in there. Sometimes it's really important that you put some water in there to absorb the heat of solution. Then you swirl it to get it to mix, and then there's going to be a line on this volumetric flask. You're going to carefully, oh, not that line, there will be a line somewhere up here in the neck. You're going to carefully fill in the water from your squeeze bottle until you get to the line, and you read from the bottom of the meniscus. You're going to be very precise because a volumetric flask is calibrated to be much more precise even than a graduated cylinder. So get it right on that line. Do not go past the line, or you have to start all over again. If you're below the line, you can always add more, but you can't take any out if you added too much because it's already mixed up with your stuff. So that's the general run-through. Let's solve it mathematically, and then of course you're going to do this in the lab. So our question says, how many grams of hydrochloric acid would be required to make a 50 milliliter solution of 0.27 molar, 50 milliliters of a 0.27 molar solution? Speaking is so tricky. Alright, so 50 milliliters would be 0.05 liters. Alright, and we want to make 2.7 molar. So I have 1 liter down here, and how many moles? Remember, molar means moles per liter. So I'm going to have 2.7 moles per liter. Alright, have I answered the question? Here's my target. How many grams? Not yet, but I'm getting close. So I know every 1 mole of hydrochloric acid has 36.46 grams. Alright then, time for a calculator. 0.05 times 2.7, then multiply by the molar mass, 36.46, and I get 4.92, how many sig figs? 2 sig figs. Alright, so suppose that you were going to do this whole process. You're going to weigh out your solid HCl and then mix it with water. This time it would be very important that in the bottom of that volumetric flask you better have some water down in here, because anytime you put acid in water it's going to generate a lot of heat. So you need water already in the flask before you put any acid in there to absorb the heat. Remember, water has the highest specific heat of any other substance, 4.184 joules per mole per gram degree Celsius anyway. So it's going to absorb all of the heat that's generated when we try to dissolve the acid in water. The acid won't have the ability to do that. So be careful. Add acid to water, not water to acid. I think I missed one. Nope, we just did that one. Alright, here's another example. What would the concentration be if you used, so concentration is measured in molarity. So here again we're going for moles per liter. If we use 27 grams of calcium chloride to make 500 milliliters of solution. Okay, so I've got to know how many moles we've got, right? So 27 grams of calcium chloride is how many moles? Well, going to need a periodic table here. Calcium chloride. Calcium is 40.08 and then chlorine is 35.45, and there's two of those. So I get 110.98 grams for every mole. And then we're going to make 500 milliliters of solution. So that's 0.500 liters, right? Moving the decimal 3 times because we're going from milliliters to liters. Grams cancels, and now I have moles per liter. Our question is asking for moles per liter. So when you get your units to look the way you want, you better stop. Remember, if you kept going past your target, you wouldn't hit what you were aiming for. Oh, doing it wrong. Divide by 0.5, and I get 0.4865, 2 sig figs. So we're going to call this 0.49 molar calcium chloride. So that's our concentration of the solution with 27 grams and 500 mils. Alright, so every time you solve a problem like this, you just do what you've always done. Go to moles. It's the most reliable thing you can ever think to do. Alright, now if we're talking about a dilution, then we're going to take something concentrated and we're going to make it more dilute. And here's the rule that we're going to follow. M1V1 equals M2V2. In other words, the number of moles has to stay constant. So if we took the molarity, moles per liter, times the volume in liters, it has to be the same as on the other side, your molarity times your volume. Notice, moles has to equal moles because of the law of conservation of mass. So if you have a concentrated solution and all you add to it now is water, then the moles of stuff in the water has to stay the same, even though now the volume has changed. So it's a proportion. You can solve it just like a proportion. The molarity of your concentrated solution times the volume of your concentrated solution has to be, in the end, equal to the molarity of your dilute solution times the volume of your dilute solution. So it's the law of conservation of mass again. Let me show you how to set this up, and I think I have the wrong example number. Ignore that. We're going to solve this example whether it has the right number or not. So we have 500 milliliters of a 3 molar hydrochloric acid solution. That's what we want to have. What we have on our shelf, though, is a 12 molar hydrochloric acid solution. That's generally what your stock solution is going to be. It's 12 molar. So how do we turn 12 molar into 3 molar? You may already have worked this proportion out in your head. So I have 12 molar times some volume has got to be equal to 3 molar times a volume of 500. And that's milliliters. Okay, 0.5 liters. Doesn't matter because your volume can be in milliliters either way. Because millimoles per milliliter might be handy for you to use instead of changing liters and milliliters all the time. Anyway, now how do we solve this proportion? We got to solve for V, right? So we're going to take 3 times 0.500 divide by 12, and we've worked it out. So we're diluting it by 25%. And I need to have 0.125, right? Yep. Liters of 12 molar hydrochloric acid to start with. Okay, so then what do I do with it? I get my 125 mils, right? And I measured out so carefully with my 12 molar. So then what do I do with it? Let me show you. I have a pretty picture. See? Oh, pretty picture. So let's say this was our 12 molar solution. Okay? And here's my hydrochloric acid. This is what's sitting on the shelf. So what we really need is not this whole entire amount. We just need to, sorry, not the whole beaker, just a small portion. We're going to take 125 milliliters of that concentrated stuff. We're going to put it in water so that now we have 0.500 liters of solution. So we're going to put this concentrated stuff in water and then of course fill the rest of the water up to the mark in your volumetric flask because we've got to have moles equal to moles. So we took our 3 molar and our 0.5 liters. We wanted to know what volume do we need here. So that was the math that we did, and this is the process that we use in the lab. And I'll show you another picture too. So we add water to the flask until it's about half full, put the stock solution into the water and fill to the line. Here's what that might look like for you in class. If we take our concentrated solution, which is shown here on the left, here's our dark blue concentrated solution, and we take a known portion out. This one shows using a 25 milliliter volumetric pipette, and then we put it into our empty flask. This is a bad example. Put some water in here. So we're going to add acid to water first. Put the water in. Then you add your acid in, and then there's a mark up here. You're going to fill to that mark with water. Then swirl it around. Put the stopper on it, and then tip it upside down, up and down, until it completely mixes. We're going to get lots of practice at doing this. You will be an expert at solution dilution. In fact, your final at the end of the year depends on you being able to do this. Fair warning. Starting over. Alright, so let's take 25 milliliters of water, and it's added to 125 milliliters of a 0.15 molar sodium hydroxide solution. What will be the new molarity of the diluted solution? So we're going to use M1 times V1 equals M2 times V2. This time I'm solving for my new molarity, so that's my M2. Let's divide both sides of this by my V2. Alright, so now I'm ready to figure it out. Molarity of my diluted solution is going to be equal to the molarity of my original solution, 0.15, and this time I'm going to call it millimoles per milliliter, because moles per liter is the same thing as millimoles per milliliter. And I'm going to multiply that by the volume of that 0.15 molar. So that was this one here, the 125 milliliters. Okay, and then we're going to divide by our new volume. For our new volume, it says we had 25 milliliters added to 125 milliliters. So if I take 25 milliliters and I add it to 125 milliliters, why then I get 150 milliliters. All right, time for a calculator. Let's do some math. 0.15 times 125 divided by 150, and I get 0.125 molar. So we went from a 0.15 to 0.125. Is that really less? Yeah, that's less. Just not a lot less. All right. That's it. That's how we work with